Hopefully it is
Yeah, it is.
moving.
It
Right?
is.
Yeah, then it's great. Okay, then we'll start. Myself Vinayak Khande, and yesterday also we met and we have discussed some interesting facts about the operational amplifier. Today and tomorrow we will discuss about the design of voltage reference circuit. Today we'll try to establish a base to understand how to design a voltage reference circuit from a scratch. And tomorrow we will discuss what are the progress and what are the uh, advancement happened in recent days uh, for the voltage reference circuits, right? Okay, then we'll start over here. What table of content? What we are going to see today are, first of all, we'll go with the basic of voltage reference. Then we'll quickly go through some popular topologies of a voltage references. Uh, Popular topology means the topologies which generally people are using into the industry, and it is almost there are only few topologies exist because voltage reference circuit is quite a tricky circuit, so that generally people don't want to experiment much in industry for designing a voltage reference, so that they are having some set topologies that we'll discuss today. After that, we'll do some feedback analysis because feedback is one of the critical part in every circuit, as it is critical for other circuit. Is similarly voltage reference is not different for that. Apart from that, I'll take one case study uh, which I have designed, simulated, even measured, fabricated into 180 nanometer technology, and measured those results that we'll discuss. And after that, I'll conclude today's presentation. Okay. These are quite basic terminologies. I think everybody must be knowing already, but just completing the formalities, I have to go with this if anybody is not knowing these terms. Sorry. At left hand side, you can see the CTAT, the voltage which is reducing with the temperature, right? Means x-axis is the temperature, y-axis is the voltage, so that you can see that voltage is falling as temperature increases, so that we can say that it is a complementary to absolute temperature. And second one is PTAT. It is exactly opposite to the CTAT, where voltage is increasing with the temperature. So that just you have to keep in mind that CTAT means falling and PTAT means raising, right? There and these terms, there this slide and next slide which we are going to discuss, it's like a characterization measures for designed voltage reference. The first one is the temperature coefficient. Temperature coefficient, generally it is popularly called as a TC, right? And uh, TC gives the measure of how much accurate your voltage reference is, right? First of all, what is meant by voltage reference? Voltage reference means some voltage which does not vary with the temperature, right? In terms of a mathematical term, if I wanted to say, then I can say that dV by dt should be zero for that particular voltage, right? If dV by dt is zero, then I can say that, okay, temperature voltage is not varying with the temperature. We can call it as a voltage reference, right? Then here I have in temperature coefficient, we'll measure that how much deviation it is getting from its nominal value, right? And generally those variations are very small, and how much small, that much your voltage reference is better, right? So that formula for that is how much voltage is, or reference voltage is varying over the temperature, divided by temperature into divided by nominal voltage, right? And after that, you have to multiply by 10 raised to 6, so that you will get the part per million by degree Celsius. Why it is getting multiplied by 10 raised to 6? Because this otherwise the number is very small, so that it's very difficult to quote anywhere. So that generally it is multiplied with the 1 mega number, right? So, and it is mentioned as a unit as a ppm per degree Celsius. And it varies with the architecture to architecture, and that ppm number. We can see that some people have quoted the 12 ppm, 10 ppm, 9 ppm, and all those things. But with the industry standard, you can go till 100 ppm, then also it is fine, right? Because even though achieving 100 ppm itself is a quite difficult task. Then right hand side, you can see the line regulation. Then line regulation is again, if in TC we are varying the temperature, but in line regulation, as it says, we are changing the supply voltage so that sorry, we can change the supply voltage and see the how much reference voltage is varying with that, and unit is millivolt per volt. Here I have mentioned millivolt per volt, but it is not for line regulation. You may find the different units as well. In some paper or some data sheet, you will find that line regulation mentioned in terms of a percentage, so that it doesn't matter. Just doesn't matter at all, because finally numbers which we want it is important to understand. These two, like 3 and 4, are DC characterization, and this fifth one is a AC characterization, where power supply noise attenuation, where we increase the voltage in terms of frequency, or we keep the voltage same, amplitude same, and vary the frequency, and see how much variation with the frequency your voltage reference is seeing, right? It is, I have mentioned as a PSNA, it is similar to the term which you used into the op-amp, which is called as a PSRR, right? Power supply rejection ratio. And in a thumb rule is that if I wanted to have a better PSNA in a voltage reference, I have to design a super duper operational amplifier, right? Means PSNA is generally governed by the operational amplifier, right? Means operational amplifier we are using in a loop while designing this voltage reference, right? And that 3 dB and this PSN is 3 dB generally matches with each other. And that you can see from this graph. Also, this is kind of a mirror image of a operational amplifier, which we have seen, operational amplifier frequency response, which we have seen yesterday, right? That is a maximum absolute percentage variation. That is a 6 term. Right hand side, you can see it is again a representation of a TC. Sometimes people write down map V, or sometimes people write down as a TC, so that it is it doesn't matter, because both those things represent similar characteristics or similar testing of our voltage reference, right? After this, we'll see the concept how to design a voltage reference. Before going ahead, here for simplicity, I have taken the NPN transistor that you can see in a circuit. But generally, while designing a circuit in IC, we use the PNP transistor. Why it is so? Because generally people use the single well process or a twin well process, right? And twin well process, you will get only PNP transistor. You cannot get the NPN transistor unless and until you go for a triple well transistor, right? And unless and until you require some specific application where whole IC should be fabricated into triple well process, people just for the sake of designing a voltage reference, people cannot go for a triple well, right? Because it is a very costly process. So that voltage reference is generally designed in a twin well process, and there you will get the PNP transistor, and that PNP transistor also is nothing but parasitic BJT. So that as it is a parasitic BJT, beta of that, it is not very well uh, designed or taken care as a fabric with the technology, uh, whether it is a TSMC or UMC, right? Why it is because they are much more concerned about the transistor performance or CMOS performance rather than the parasitic BJT performance, because parasitic BJT is generally used for a voltage reference only, right? And as voltage reference is generally considered as a uh, DC circuit, so that people don't bother about much to put the extra effort while designing the or when fabricating the PNP into the foundry, right? So that's all about the PNP. But yeah, you have to keep in mind that this PNP is a parasitic, and beta of that parasitic is quite small, right? Because generally the transistor which you have seen in lab, it is having the beta of around 100, 200, 300, and this beta is lies around 2 to 4, which is quite small. So that, and we don't want actually amplification, right, out of this parasitic BJT, so it's okay. Right? Then if I take that BJT and tap the VBE by pumping the current I1 into that, then I'll get, if I increase the temperature, right, I'll get response something like this. And roughly it is observed that the slope of that is minus 2 millivolt per Kelvin, right? Then this is a well-known fact that if VB reduces with the temperature by the slope of minus 2 millivolt per Kelvin, right? If for particularly band gap based voltage reference, the reference I have uh, used is Razavi and Paul Greimer, because Paul Gray is having much more detailed explanation about the voltage difference. If anybody wanted to go a little bit deeper, I think they can read the Paul Gray. Okay, then what people generally do is that they connect transistor or multiple transistor into the parallel and pump the exactly same amount of current, right? Here also I have pump I1, here also I am pumping I1. Because of that, what response you are getting is VBN, right? And I'll not
Uh,
get into
sir,
detail.
uh,
Yeah,
could,
yeah, please.
could you please click on the hide? There is something like in the Google Meet.
Okay, okay, right. Fine. I
Thank you,
think it
thank
is fine now, right?
Yeah, yeah, thank you.
Okay, thank you. Thank you for notifying that. I was also not aware of that. Sorry. Thank you. Okay. Then VBN, if we tap, then slope of the VBN is quite steeper compared to the uh, single transistor, right? And that just now you keep in mind that if I'm having the single transistor, slope is minus 2 millivolt per Kelvin. If I'm having multiple transistor connected into parallel and pumping the exactly same amount of current, then the slope will be steeper, right? Why steeper? You can read some device books. Then we try to understand what we want and what we have, right? And what we are having is that this red curve, right, that we have is minus 2 millivolt per Kelvin, that VB1, and we need or at the end, what end result we wanted as a green, where voltage does not vary with the temperature, and we need something like this, right? Means what we have is we are having two information. One is that VB1 how it varies with the temperature, and VBN how it varies with the temperature. And now we know that, okay, what we want. So that it is important, it is a little bit philosophy, you can say that we have plus we need what we want, right? So that okay, then VB1, and then some smart guy came and he said that, okay, if you do some subtraction between VB1 and VBN, you'll get something which is increasing with the temperature, which is matching with your need, right? then this is what we needed. So that delta will be what we needed, right? So that we are having some positive slope there. Delta V has some positive slope with respect to temperature, right? But again, you have to keep in mind that currents are exactly same. Okay, then again, same thing. I'm having delta VB increasing with the temperature. But if we look at carefully, whatever we needed is something much more steeper, right? Steeper in upward direction, right? So that delta VB need to be scaled to get this, right? So that if we add we need plus we have, then we'll get the voltage reference which we wanted, right? Then here what we can do is that if I'm having the delta VB, which is dotted line, if we scale it by the factor of S, then add it together, we can get the straight line. That is VB1 plus S into delta VB is equal to V reference, right? Here we are trying to establish a math or what you can say concept behind before designing exactly what voltage reference is, right? Then how to find the value of S? That is the question, right? Then we can do some quick and easy math. Is that what we wanted? We have to actually what we have to do is that we can take a derivative, right? And slope of VB1 and slope of delta VB that we'll try to equate, right? At the end, what we wanted is delta VB slope should be exactly opposite of uh, VB1 slope, right? And I know that VB1 slope is minus 2 millivolt per Kelvin, so that S into d by dt into delta VB should be 2 millivolt per Kelvin, right? And if I put the number n is equal to 8 and measure the means at the T at room temperature, then I'll get S is equal to 11, right? Then now I got the value. What is the value of S? Then I can revisit this equation, top equation, and plug the value. That is VB1 plus S into delta VB is equal to V reference. VB1 we know that 700 millivolt plus 11 into 26 millivolt ln N. This delta VB is nothing but VT ln N, right? It is coming around 1300 millivolt. It is called as a band gap based voltage reference because generally as it is close to 1.1 electron volt of a silicon's band gap, so that and generally it doesn't vary with the temperature, so that it is called as a 1300 it is called as a band gap based voltage reference, right? Now, a similar thing I'm showing over here, VB1, I'm having scaled S plus delta VB where S is equal to 1 and I'll get 1300, approximately 1300 millivolt, right? Now here, what I'm trying to establish some general equation which I wanted to do. VB1 I have assumed as a VA, VBN I have assumed as a VB, right? So that I can write the equation like a VA plus S into VA minus VB is equal to reference voltage. And VA plus S into VA minus S into VB is equal to reference voltage. Means why I'm writing all these elaborated steps? Because at the end, what we wanted is some amplification of this, right? Means we'll start designing a circuit now. Till now we have till now we got the concept, means what we required or what we want. From that we derived some mathematical expression for that, right? And now I wanted to implement that into actual circuit, right? So that what if I'm able to uh, design this equation in terms of a circuit, then it is done, right? Then we can get the final reference voltage, which does not vary with the temperature, right? Means as my advisor used to tell, if you can uh, formulate something or you can say something into the English, you can always make a circuit out of that, right? So that now we have formulated into English what we want, and now we go for designing a circuit, right? Then what we want S into VA first. We cannot implement all the equation uh, at the same time. We'll go step by step. First, we'll implement S into VA. S into VA means some scaling of VA voltage. That means in electronic term, we can say that we wanted some amplification of a VA voltage. And how to do the amplification? Generally, generally, what we can do for doing the amplification is that we can simplest thing is that we convert that voltage into the current, right? Suppose I'm having the voltage 1 volt, I made it into the current by connecting the 1 ohm resistor, 1 ampere current I'll get, right? And same current if I push into the 2 ohm resistance, right, I'll get the 2 volt, right? So that it is nothing but a amplification. Means step is that convert the voltage into the current and made it flow through the another higher value resistor. Here same thing we are doing. For converting the voltage into the current, I have used some operational amplifier and a voltage controlled current source, that is a MOSFET, right? So that as op amp, assuming op amp is having uh, very large gain, uh, a large open loop gain, and we are operating at a very low frequency, so that this voltage will be VA. So that current which is flowing through this resistor or this complete branch is nothing but VA by R2, right? Now we are able to convert the voltage into the current. Now, as we have decided previously, same current will try to flow it to the higher value of resistance. That is, now it is a R3, right? Now R3 by R2 into VA. And we wanted to design a circuit which scales the voltage VA, that is S into VA. Means if R3 is larger than R2, means R3 by R2 is 11, then our equation is satisfied, right? That means we have done amplification, right? But if you look at the equation, we don't want S into VA, we want S into VA minus VB, right? So that what we can do is that uh, instead of connecting the VA, here it was a VA, so that I can connect VB over here into, you can see the battery polarity, and it is a VA minus VB, so that it's fine. The current I have to change, it is not a VA, it is VA minus VB. Okay, then so current, I made a mistake, then that's all right, I'll go ahead. Okay, but as I said, if we look at the circuit carefully, I have connected the VB. I can move the VB into this direction instead of connecting the voltage source into series, right? It does not make any sense. So that what I can do is that I can put that VA into, that we can remove that VB and put into the VA by just following direction of the arrow. Nothing changes, right? So that for that matter, I'll get amplified version of VA minus VB, right? But again, if you look at carefully the equation, we don't want S into VA minus VB, we want plus VA as well to get the final reference voltage. So that easy thing is that just I put VA over here, so that at the end we can get S into VA minus VB plus VA. Okay, fine. Uh, But now somebody will argue that okay, this all the batteries you are connected, uh, but if I'm having the battery, then what is the need of reference voltage, right? At the end of the day, we were designing a voltage reference because we wanted some voltage which does not vary with the temperature inside the IC, right? Then all the batteries we are connecting, then this circuit does not hold true at all. Then at the end, we'll replace all the VB1 with the batteries with the BJTs, and we rewrite the equation. And this is a VBN, VB1, this is VB1, and S into delta VB plus VB1. Means at the end, we got complete our reference voltage over here, right? But still, if you go and simulate this circuit, it will not work at all. Why it will not work? Because our basic fundamentals, which we have started with, is this assumption that both the transistor is having the equal amount of current which is flowing through this, right? So that we can go back and see that, yeah, it is the current which is flowing through this is V minus VB by R2 here actually, V minus VB by R2, but no current is flowing through VB1, right? So that what we can do, it is a simple thing, made it flow the current through that transistor also, right? So that just I have mirrored one transistor and made the current flow through that transistor. That means now the circuit, if you go and simulate, it will work. Uh, it will work, uh, but in generally in simulation, definitely you'll get the voltage approximately 1200 to 1300 millivolt, right? Uh, but uh, but still this design is not complete, right? Why it is not complete? In next few slides we'll get to know that, right? Because while simulation, this if you go and simulate the circuit which you are seeing on a screen, definitely it will work on a simulation, but once you go and fabricate it, then it is having a 50% chances that it will work and 50% chances that it may not work, right? So probability of working of a fabricated circuit of this shown diagram, it is having probability is 50%, right? Why it is so and how we can make it 100%, that we'll see uh, in next few slides. This is the one approach where we can go from concept to circuit. Another approach we'll see, that is also quite interesting. We know that the circuit or equation, what we wanted to realize, this VA plus S into VA minus S into VB, right? Then again, same thing, S into VA is nothing but amplification, right? Then I can go and straight away pick one operational amplifier and select the value of resistor like Sx minus 1. Actually, it is Sx I have to written. Anyways, Sx minus 1 into R divided by R, then I'll get the uh, amplification by the factor of Sx, right? Then, but we don't want actually S into V. We want something S into V minus VB. So that just as I know that this circuit looks like a subtractor, then I can put the VB over there. Then I can go ahead and I can derive the circuit, derive the equation. And this equation something look like very familiar to us. That is VA plus some scaling factor minus into difference of VA minus VB, right? So that is something which already we have seen, right? Some VB1, I can replace VA with the VB1 and VB with the VBN, right? And this is scaling factor. Why this I made this Sx minus 1 or Sx particularly instead of S? Because this scaling factor and that scaling factor is having little bit difference, right? Because this is reduced by minus 1 factor. That is the only thing, nothing else. Right? Then again, I can remove those batteries and replace it with the transistor. This is a N actually, I missed the writing, N bracket N. Okay, this is VBN and this is a VB1, right? But still it is not complete because if you simulate this, like, it will not work because again, the current which is flowing to this transistor and current flowing to this transistor should be same. And if you look at the VB1 or Q16 transistor, it is connected to high impedance node of this operational amplifier so that there will not be any current at all, right? So that is like it will not work in the simulation also. Forget about the foundry, right? Then what we can do, simplest thing, right? The our concern is that current flowing through Q15 should be same as a Q60. But here current itself is not flowing. So what we can do is that we can connect whatever we have done with the upper branch, we can connect similar kind of lower branch also, right? So that if you see that how current which is flowing through on top branch and current flowing through the bottom branch will be exactly same because two node voltages are exactly same with each other, right? These two node voltages, inverting and non-inverting, are are exactly same, assuming your operational amplifier having the quite high open loop gain, and this voltage is common to both the resistors, right? So that uh, our concern of identical current flowing through transistors is completely valid, right? Okay, I think, and whatever we have got the concept of the circuit, it was exactly thought by the Kujik in way back 1973, right? Means I believe what we thought him also might have thought similar in a similar line, so that you can see this circuit into the uh, what you can say in the paper. I think JSSC he might have published. JSSC or ISSC, I don't remember, but you can find Kujik's voltage reference 1973. Just you can Google it, you'll find this circuit. It is quite popular circuit. Okay. Before going ahead, I'd like to take few questions. Uh,
Any questions from participants?
yeah, any questions from participants?
Sir, can you elaborate more on twin well process?
Oh, okay. Uh, Twin well process means generally it is a similar process which we are having a substrate and we are having a wells for drain and source, right? That you are having the P plus region. If I'm having the PMOS transistor, you are having the P plus region, right? For drain and source. Are you getting? If I hope I'm
Yeah, yes, yes, yes.
able to make you visualize that, right? Then consider the PMOS only. You are having a
Hmm.
P sub, you are having a drain of P plus and a drain of P plus and source of P plus. In between, you are having a gate, right? But but as it is a P sub, you have to have some veil, right? To that veil is nothing but N veil, right? So that you are having a P sub N veil P plus for drain and source. Are you getting? Then because of that, it is called as a twin well process, right?
So substrate can be connected with another signal, maybe like that. Substrate can be utilized. Is it so?
No, for what you are talking about, the which
Uh,
where it can
uh,
be utilized.
so substrate is can be utilized with some other signal. Is it like so or substrate terminal?
You are talking in reference to parasitic BJT or in general twin well process.
In general, twin.
Substrate generally you have to connect it to the ground, right? Because as it is a twin well process, there is not a separate well for NMOS transistor, right?
Oh,
Then for
okay.
all NMOS, it is a substrate itself is a bulk or base. So you
Oh,
cannot connect anywhere other than the ground.
okay, okay, sir. Thank you.
Okay. Yeah. Uh, Anyone else?
And sir, what BJT you mentioned, they are only parasitic, not MOS like, not a separate device. Is it so? Only that
It is a
parasitic.
no, no. It is a separate device, but it is not. You if you go into the Foundry model files, you'll find the BJTs, but those BJTs are parasitic BJTs. As we don't have a triple well, we cannot fabricate the NPN, right? Because we are
Yes,
having only two P and one N. So that always
yes.
we can have a PNP. We cannot have an NPN unless and until we can go for some
Triple.
extra welding process.
Okay, okay, fine.
Uh, Anything else?
Hello, sir.
Yeah, yeah, please.
Is this similar to the diode connected transistor, like transistor in saturation mode, the parasitic BGT which you recently explained?
Yeah, actually, it is similar to that. Exactly,
Okay,
you have pointed out, Mr. Bose. But
okay,
here it is in BJT, we I think changed the region, right? In BJT, if it is a diode connected, it is linear region.
Right,
In
right.
MOSFET, it is a saturation region.
It's in saturation region, the amplifier, right?
Yeah,
And
MOSFET is a
one,
saturation region. It is in
yeah,
linear.
right,
Yeah,
right.
please go ahead.
And one more thing that you recently explained about the twin well process, is it quite similar to the twin tap fabrication technology of CMOS?
Yeah, it is similar. Just it
Exactly
is,
same, right?
yeah,
The substrate is by default P type, right? One N well
yeah,
is
right.
created, another P well is created. One for NMOS, another for PMOS, right?
Uh, no, P well is connected only for. Okay, P sub is connected, right? Yeah, P well
Okay.
sometimes
Yeah, right, right,
it varies with the foundry to foundry, but yeah, in
right,
general
right.
it is a P sub, N well, and in N well you'll make a PMOS.
Okay, okay. Thank you. I got it.
Yeah. Okay. Okay, then I think if there are no more questions, we will continue with this. As I said previously also, if you go both the circuits which we have designed till now, if you go and fabricate, it is having only 50% chances that it will work, because then what is the reason behind that? There are certain requirements that we have to fulfill before going into the foundry. Uh, and why those requirements are coming, it is given by the equations, right? This is a fundamental equation which we can see in normally in the book, that is a VBE is equal to VT plus ln I by IS. IS is a reverse saturation current, I is a forward current. I think it is well known fact. Okay, but again, this equation is approximated equation. The almost correct equation, you can say that VB1 is equal to VT ln I by IS plus 1, right? And for VBN it is nothing but VT ln I by NIS plus 1, right? And if after considering these two equations, if I form or if I plot the delta VB, then delta VB is nothing but VT ln N I plus IS divided by I plus NIS, NIS, right? Then for if I evaluate the I is nothing but delta VBR, and substitute those values of a delta VB here, then for I'll get the two solutions, right? The solutions will be valid if I substitute the value of I is equal to 0, then also it is valid, right? If n I is equal to 0, then this will be the ln 1 will be 0, so that I is equal to 0. And if you put I value is equal to delta VBR, then also I'll get I is equal to delta VBR, right? So that we are having the two solutions for value of I, and that is the point of contention while designing a circuit of the band gap based voltage reference, or any CMOS based voltage reference as well, right? Then why it is coming? Because your operational amplifier, if we can see into the circuit from the circuit perspective, is that if you see closely, this operational amplifier is happy when inverting as well as non-inverting terminal are at same potential, right? So that when you start the circuit and ramp your VDD while testing your chip, you will ramp it from a 0 to VDD. That's generally process. Even though if it is not ramping, connecting the voltage source directly, it is also considered as a step response. It is also kind of a ramping with the um, uh, t is equal to 0 instant, or delta t is very, very small, right? So that once you ramp the 0 to supply voltage from 0 to VDD, it is having chances that operational amplifier will be happy to make this inverting as well as non-inverting terminal to stack to the 0, right? And because op-amp doesn't know that he has to work, or she has to work, I don't know, right? Uh, op-amp doesn't know he has to work, right? So that because both the terminals are exactly at similar voltage, so that he'll be sleeping happily, right? So that and circuit will not function at all, because Q3's collector will be connected to 0, R2's this terminal is connected to 0, so that no current is flowing through uh, both any of the transistor, any of the circuit in fact, even though you have reached a VDD, right? Because Q14 and Q19, both these transistors gate will be connected to VDD as current is not floating, current is not flowing through the transistor, so that bottom part, you can say that bottom part of the circuit is connected to ground and top part is connected to VDD, so that no current will flow and your circuit will be not at all functional. And this is exactly the solution for I, that is I is equal to 0. And but we don't want this kind of scenario to happen, so that what we have to do is that we have to wake up this operational amplifier, right? How to waking up, how to do this waking up the transistor? Just you have to wiggle one of the op amp's terminal, right? Means somehow we have to create the difference between the inverting and non-inverting terminal of an operational amplifier, right? So that op amp will say that, oh no, something is fishy, I have to work, I cannot, it is not the time to sleep, so that he'll wake up and he'll do the job. And next time when these two terminals, inverting and non-inverting terminal, will be exactly same, that time he'll sleep again, right? And that time your next stable state it will reach, that is delta VB by R, right? That is the next solution. Means your circuit will be having the current either I or delta VB by R, right? So that how to make sure that, just I have connected, this is just symbolically I am showing that R7 and R1 is connected connected into the series, and here I have connected the switch, and I'll just switch on and off this, switch off and on and off this, right, for a moment. Then I'll make sure that there will be difference between inverting and non-inverting terminal, and it will rest to the delta VB by R current, right? That is the next steady state from I is equal to 0, right? Then I'll get the required reference voltage. So that is called as this, actually this operation called as a startup operation, right? And it is extremely mandatory while designing a voltage reference. Otherwise, you know what are the consequences. How to implement this into the circuit? We cannot connect the switch or something like that. People may connect, but yeah, generally it is not advisable to connect the switch. It's having its own disadvantages. Why those disadvantages that we can see later on. But yeah, how we can implement the startup circuit? There are 3 transistors for startup. This is just one circuit. You'll find that zillions of circuits for designing a startup circuit, right? I have used the 3 transistor, MST1, MST2, MST3, right? And here I have to wiggle this node Vx, right? At initially Vx will be 0, Vy will be 0, and everything will be sleeping, right? And at MST1's drain also will be connected to VDD, right? Because no current is flowing through this. And MST2's gate is connected to ground, right? And MST3 is this terminal, gate is VDD, drain is VDD, and source is at ground, right? That means at when your circuit is about to start, means when you are ramping the voltage from 0 to VDD, MST3 will start conducting, and that is the time your Vx will get wiggled, or it will get away from a 0 voltage, right? And but startup circuit, it adds its name indicates it should only start, and after that it should stop, right? The circuit should get disconnected, and MST3 is designed in such a way that when Vx will reach its steady state, that time Vx will be 700 millivolt, and you will make sure that VST3 will be switched off, right? So that this transistor will help us to design make sure what VGS it should have, or gate voltage of this MST3 should be. Suppose this is 700 millivolt at a steady state, then you have to make sure that this will be 500 millivolt or something, so that this transistor will be having VGS of minus 200 millivolt. That means this transistor is switched off, means whole startup circuit is now cut off, right? This is one trick to design a startup circuit. And as I said previously, it is very much important to design a very good startup circuit. I have seen few examples where because of the startup circuit, whole chip is is getting failed. Now we can see we can quickly go through the circuit which people are using quite popularly nowadays is presented way back in 1999. That is famous Banbaz architecture, and you can find this architecture in JSS 99, right? And this architecture is nothing but a current mode architecture. And why this architecture is popular? Because it works on a sub 1 volt, means 1 volt or below to that, right? Uh, it is having one question is that if my reference voltage itself is a 300 millivolt, right? You can say that here my reference voltage itself is a 300 millivolt. How can I can operate at the VDD lesser than that, right? That is also one of the interesting point to observe over here. But here, what we can do is, or what Banba has done is, he has scaled that also by the factor of some value. Right here, I have not shown that video. Here actually VB also is must be getting scaled by something. Yeah, R3 by R1, right? This VB is getting scaled by R3 by R1, R3 by R1. I have selected as 1. Okay, that mistake I made. Okay, anyways. Okay, this is a current mode approach. Instead of everything talking about voltage, what Banba said is that you talk or think about the current, so that he converted that uh, emitter voltage or base emitter voltage into the current, right? And as previously we said that we can use for we can convert the voltage into the current and made it flow through the higher value of resistor for amplification. Same way we can do for attenuation as well. We convert the voltage into the current and made it flow through the lower value of resistor, so that we'll get the attenuation. Similar thing he has done. He converted the voltage into the current and made it flow to the another value of resistor, and he has scaled by the factor of lesser than 1, right? So that you can get the scaled band gap based voltage difference, right? And as your reference voltage itself is operating at the scaled version of actual band gap based voltage reference, so that you are having the luxury that you can operate at the lesser VDD, right? Same thing is happening because you know that this node potential at a room temperature 700 and 700, right? You can design your voltage reference is around 850 or something if you want. As it is R3 is there, you can scale it to any value, right? And this transistor, now this is 700, then you can have a VD set of margin of 300 millivolt. That is also quite high, in fact. But yeah, Banba has proven that you can operate your band gap based voltage reference concept at a 1 volt as well. Fine. Another thing which Banba's architecture is modified further in JSSC 2002. What people have done is, you can see the difference here. Banba has used a NMOS differential pair, right? So that it is having some limitation over the input common mode range, right? To avoid that limitation, what uh, actually this is Long's architecture. I have not mentioned his name, but yeah, what Long has done is he has divided that resistor into two resistors connected into the series, right? And connected to the PMOS base voltage reference, right? As this voltage is down to or at the lower rail of a supply voltage, you can easily drive the PMOS differential pair with the high common mode input common mode range, right? So that this architecture is also quite popular. Only problem with this kind of architectures, both architectures, you are having the resistance, you are using the resistance heavily, so that if there is a mismatch between the resistors, then you have to bear uh, those variations in the resistance, right? Uh, After that, many other derived version of these circuits also came, which how they can tackle the resistor mismatch. But fundamentally, the skeleton of a circuit is bandpass architecture and Long's architecture, particularly bandpass architecture, because bandpass architecture has given the breakthrough, uh, where he said that you can work at a VDD is equal to 1 volt, and VB, band gap based voltage reference, you can scale below 1200 millivolt, 1300 millivolt to 700, 600 millivolt. I think he has shown by the 450 or 500 millivolt. You can refer the paper. It is a quite nicely and well written architecture. Okay, one more approach for a band gap based voltage reference. This is a basic design concept. Yeah, 1 second. 1 second, I'll grab some water. Now, here is a quick question to the audience. What is the middle potential of, if I wanted to tap, or if I wanted to measure the voltage at the middle of these two voltage reference, two current sources, if I1 is exactly similar to I2? Anybody can take a challenge. You can give a wrong answer as well. It's not an issue.
We discussed this in just the previous session
Oh, okay, that's great.
while discussing CMFB.
Okay, 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 okay. Okay, that's great. Mm. Anybody among the participants?
Can you just show the slide? Maybe then.
Yeah, please, 1 second. Yeah.
Yes.
I hope it is VDD by 2.
If it is I1 is equal to I2. Current source is that is correct answer. But if current source is very much ideal, then what you can say? Okay, 1 second.
Hello, sir.
Yeah, please go ahead.
It is VDD only.
It is a VDD only. Okay. You're close to the answer, but not. My question is that if both the current sources are ideal and I1 is equal to I2, you can assume that there is a smaller capacitance at that node, right? Connected to the ground. That also we can think of. Right. If capacitor is connected over here, like this way, not able to show. I don't have pen. Yeah. If I1 is equal to I2, then what it will happen if that current will not go at all into the capacitor, right? how much current coming from a top, it is getting sucked by the bottom, right? So that if I'm connecting the capacitor here, so capacitor does not have any current which is flowing through that, so that it will not charge at all, so that voltage is nothing but a zero. It is called as the AC ground, which you can say, right? And if I2 is larger than the I1, then what will be that middle potential? It is similar. A capacitor will charge by that I2 minus I1 value till the infinite time, right? So that it will stuck to the VDD, right? If I2 is greater than I1, the middle potential stuck to the VDD. If I1 is greater than the I2, then this potential will stuck to the ground, right? Okay. Now we'll go with just I wanted to refresh those things. Now again we can go to the diode equation. Diode equation is nothing but I is equal to Is exponent Vb divided by Vt minus 1. This is sorry approximately higher order equation, we can say, as generally in approximation this minus 1 will not be used into the equation that you might have seen previously or in a books as well. Sorry. Then what is the value of I1 and I2? I have written over here. I1 value is nothing but Is exponent Vx minus Vt. Vx is nothing but a VBE of this transistor. And I2, again, this is a voltage across this is nothing but Vx minus I2 into R, right? So that I2 value is Is into exponent Vx minus I2 into R, means voltage drop across this resistor divided by Vt minus 1, right? And what we want to make is that I1 is equal to I2 is equal to R. If somehow, if we're able to make I1, both these currents, that is I1 and I2, exactly matched with each other, right? Then I can get delta VB by R, right? This concept is already we have studied. Just we have, I have just twisted the sentence and I have written over here. And previously we made sure that current flowing through, I'll show you that. Yeah, current flowing through this VB1 and VBN should be exactly matched with each other so that you can design a delta VB which is increasing with the temperature. That is a PTAT, nothing but. Means if you wanted to design a PTAT voltage, you should have a two dissimilar transistor in the, which is having the identical current is getting pumped, right? So coming back to the slide. Yeah. Then when we wanted a PTAT kind of behavior, that is delta VB by R, then the current flowing through, then this I1 is equal to I2 should be exactly matched with each other, and we can say it is I. This is just reverse way we are conceptualizing similar thing. Then if I connect the battery of Vx and vary from a 0 to very, very high potential, then what will happen? If you solve this two equation, what you can find is that when I1 is very, very smaller than I2, right? That means Vx is small, right? When Vx is small, then I1 is smaller and I2 is larger, right? From this equation also you can figure it out that. And when Vx is large, then I2 is smaller, I1 is large, right? When Vx is large, you can see over here. When Vx is large, then I1 is large. If Vx is large, it is having some drop across this, that is I2 into R, right? Here we don't have any drop, so that if Vx is very, very large, then definitely I1 will be larger than the I2, right? That means what we are trying to establish is that if I am varying the Vx from a 0 to very, very high value, initially I1 will be smaller and over the time I1 will be larger than the I2, right? Then what in English what we can say is that there is some potential for Vx where I can have the chance to get I1 is equal to I2, right? From here you can see that. If I1 is smaller than I2, Vx is small, Vx need to be increased to achieve that I1 is equal to I2. If I2 is smaller than the I1, Vx is large, then Vx need to be decreased. Right? Now I think fact is established. If I connect the battery, nothing will change, right? Whole our argument is still valid, even though if I'm connecting the battery into this, because at the end, I have connected the battery such a way that in KVL it is getting cancelled, so that it doesn't matter at all whether I have represented this circuit or I have shown this circuit. Then I can replace the battery with the transistor, right? Where VGS is same for both the transistor, right? So battery is nothing but a VGS, so that I can replace that batteries with the VGS, so that nothing is changing. Nothing changes for changing for this as well. Now what I do is that somehow I get the current source I2, and I try to measure the voltage of VY, right? Then forget about the Vx at this point of time. Then I know the concept. If I2 is greater than the I1, that middle potential will increase, right? Same way we can see over here. If I2 is smaller than the I1, Vy decreases. This is a higher current and this is smaller current, so that Vy will decrease, right? And move towards the ground, right? And if we go back into previous slide, when I2 is smaller than the I1, Vx is large and Vx need to be decreased, right? And similarly, we said over here, if I1 is smaller than the I2, Vy will reduce. And exactly opposite, if I1 is smaller than the I2, Vx is small and Vx need to be increased, right? Then actually, if we see closely, Vx and Vy are moving in the same direction, right? You can see that. If I1 is smaller and I2 is larger, Vy will fall down, and that means Vx is small, I have to increase the Vx, right? So that what we can do is that I can just short it together because it is behaving exactly in a similar fashion, right? So that I can remove this battery and I can short it over here, right? But still, from where I can get this I2, because I2 is flowing here. Here I2 have just symbolically have represented over there. But I know how to get the I2 over there. Just I can mirror this I2 into this direction. So that whole this circuit is now complete. And I can say I1 is equal to I2 is equal to I, because this loop itself will make sure that I'll get I1 is equal to I2 is equal to I. And this is nothing but a p-type current I can design. And once I know the p-type current, how to design a p-type current, I just know how to design a band gap based voltage reference as well. Right, then this is a conventional band gap based voltage reference. Previously, we have used the operational amplifier, but now I have used a very large length transistor. Generally, we use the large length transistor so that we can get enough loop gain over here to stabilize this. This means to get this KVL right? And this is nothing but a BGR. We have analyzed this concept with a different approach, right? And with a similar token, whatever we got from a p-type thing, we can remove this BJT from the bottom, right? I can connect that to the ground here, right? But somehow I have to compensate this R3 drop with the MOSFET, right? So that I have to increase the width of this transistor, that is Q19, right? So that I can accommodate the drop of R3. Are you getting? Because this VGS is suppose 500 millivolt, this VGS also is 500 millivolt, then there will be no drop across the R3, right? So that for accommodate that drop, what I can do, I can make it as a 500 millivolt. I can make this 400 millivolt by increasing the width. And this R3 I can, and because of that I can have the current flowing through the artery. And this circuit is quite popular with the name of constant GM bias circuit. And this is almost almost all the circuits you will find that this constant GM bias circuit is used for designing the bias circuits. BJT version of this of constant GM bias circuit is called as a beta multiplier. I think that term you must be quite aware with. But that beta multiplier, if we try to realize with the MOSFET, it is called as a constant GM bias circuit. And beauty of beta multiplier or a constant GM bias circuit is that your current does not vary with the supply voltage, right? So that it is a supply invariant voltage reference you can get. Then things to remember before proceeding ahead. I am having the simple op-amp. Generally, whatever op-amp you are using while designing a voltage reference, you don't have to go for a two-stage amplifier or three-stage amplifier or or four-stage or something like that. It is not at all needed because first of all, this circuit is kind of a DC circuit, so that you don't have to bother about the frequency variation much. So that you can realize the amplifier with a simple differential amplifier. Then somebody will ask the question, if simple differential amplifier, then how the loop gain is getting satisfied, right? Then there is a question is that it is not a single stage amplifier as you think of, because this M2 and R and all these branch also is contributing to the gain, right? So that even the operational amplifier is single stage, whole loop gain will be a two stage. So that whatever we do for stabilizing the two stage amplifier, we have to do similar kind of thing to stabilize the this band gap based voltage reference connecting the heavy value capacitor and all, right? So that while designing a band gap based voltage reference, don't go for a fancy op amps because otherwise you'll get into the trouble of stabilizing your band gap based voltage reference. Now, as small signal analysis, sorry. Yeah, small signal analysis. Oh, sorry, I'm troubling with the cough. Yeah, this is small signal analysis for now. It's fine, I guess. Thank you. Yeah, small signal analysis, I think it is quite mandatory for analog designer. So it is true for voltage reference as well, right? Because we are using the operational amplifier and it is a frequency dependent component. And interesting fact is that all the devices, whether it is a linear or non-linear, we are having some linearized model for that, so that we call it as a small signal, right? So that this BJT also having its respective linearized model, which we call it as a resistor, right? So I can replace all the BJTs with the resistor for deriving the small signal or for doing the small signal analysis, right? But interesting fact, if you note that how much the area your BJT is having, small signal resistance is exactly same for both the transistors or both the BJTs, right? You can go back and check this fact. I think you must be already aware of this fact, right? Small signal resistance of a BJT or a diode, in fact, for a diode which is area is 1 and area is 1 million, small signal resistance is exactly same. So that this is quite interesting fact. With this, you can go ahead and replace all the BJTs with their small signal equivalent resistance. Now as we have connected the operational amplifier, there are two paths for feedback. One is that this path and second one is this path, right? Then we have to analyze that, okay, then as it is positive sign is connected there, then there must be a positive feedback. Then we may get into the trouble, right? Then we'll understand that how it is happening. Right? If I increase this, for studying the loop, generally what we do, we break the loop and study the loop, right? Then I'll increase first I'll see the left hand side. I'll increase the uh, gate potential by some delta V, right? For this transistor, then how much I'll get voltage over here. It is in a negative direction, that is minus GM14 by R1, right? Assuming R0 is quite large than R1. And similarly, here what you will get is, again, you are reducing the voltage, so that here also you'll get something minus GM9 into R2 plus R7, right? But if we look at closely this dotted arrow, if this R1 is getting fed back to the this arrow, whatever arrow is getting, sorry. Yeah, this arrow is, again, if I'm giving to the non-inverting terminal, it will changes its direction. Here also I'm giving it, sorry, inverting terminal. Here I'm giving to the non-inverting terminal, so that whatever arrow direction remains same over here, right? So that if we look at closely with these two arrows, dotted arrow and a solid arrow, for both these cases, we can see it is increasing for blue, and it is increasing as well as decreasing in for red arrow, right? That means red arrow is nothing but that operation is indicated by the red arrow is nothing but a negative feedback operation, right? And here both the arrows going into the similar direction, so that we can say it is a positive feedback, right? So that what fact you can understand with this is, here, even though if I'm giving feeding back of operational amplifier's non-inverting terminal, it is giving the negative feedback option. Means what you have to study the loop. It is not that if it is feeding back your voltage to a non-inverting terminal, that means it is a positive feedback. It is nothing like that way. You have to study the loop and figure it out how that loop is behaving, and it by that way you can say that, okay, this is a negative feedback action. It is not just it is connected to the non-inverting terminal, that means it is a positive feedback, right? And surprisingly, this is a nice example. Here in band gap, it is fed to the negative non-inverting terminal, but still it gives the negative feedback, right? Then from this, we can say that I am having two feedbacks now. One is a negative feedback and second one is a positive feedback. Then how to study those things? Then I have replaced all this with the equivalent resistance. And as I said, even the diode is area of 1 or diode area of n, it is having the equivalent resistance, right? So that here, if I give some voltage that you can see in a solid line, right? I'll get heavy, what you can say, gain at non-inverting terminal will be quite high as compared to gain of inverting terminal, right? Are you getting? Because here GM14 is getting multiplied only with the R1. Here GM9 is getting multiplied with the R2 plus R7, where R7 and R1 are exactly matched with each other. So that this voltage, what we are getting over here, it is the GM into R times larger compared to this, right? So that this, which is shown in a negative feedback, is a red arrows is a negative feedback, which is stronger than the positive feedback. That means whatever its written is same thing. Positive feedback is a weaker than the negative feedback. So that thereafter it is quite important to understand the stability as well as the functionality of band gap based voltage reference. I'll go quickly to the case study, and I hope I am having 15 minutes. I'll try to cover it within 10 minutes so that I can keep it for 5 minutes discussion. This is just a basic of voltage reference, CTAT, PTAT, and again scale PTAT, and we added one entry. It is already done, right? And how to generate a CTAT voltage. And is that, as we said, VBE, we can use it for generating the CTAT voltage, or VGS also we can use it for a CTAT voltage. If I'm using only transistor or CMOS to design a voltage reference. Mind you, if I'm using the band gap voltage reference as a terminology, then generally it is assumed that you are using the BJT or parasitic BJTs to design a voltage reference. If it is a CMOS voltage reference, then generally it is hidden fact that you are using only CMOS, not a BJT for voltage reference, because thereafter it is not a band gap kind of thing. For generating the PTAT voltage in BJT, you are having small and big transistor. Similarly, you can use the small and big CMOS to or NMOS to design the PTAT voltage as well, right? And if we derive this, one fact here is that I made this CMOS transistor worked into the weak inversion region, so that weak inversion equation of a MOS is exactly matches the linear region of a BJT, right? So that it is having exponential characteristics similar to each other, right? So that VP tat will be VT ln of M. M is just a number, right? And the difference between ratio between these two transistors M1 and M2. So after looking to equation itself, you can say that it is a process and VDD independent. Why it is VDD independent? It is nothing but a constant GM bias circuit like a thing, right? And this is a thermal variation. This is VT is nothing but a thermal voltage, so that you will not find the process and VDD variation, right? But CTAT voltage, either it is VEB or a VGS, right? And VEB is less process dependent, but VGS is heavily process dependent, right? If I wanted to generate a CTAT voltage using only CMOS, it's very, very difficult to nullify the process dependency, because at every corner or cross corner, it will change its VGS quite significantly. And then that is a challenge. Then how we have deal with this challenge? We have taken these two transistors. One is a high VT transistor. You can see the oxide thickness is larger, and low VT transistor thickness is smaller, right? And I have created the delta VGS out of that. And if we solve this equation, we will find that delta VG is nothing but approximately equal to delta VTH. And that means difference is positive, but slope should be negative. Then only it is called as a CTAT, right? So that we have taken the derivative. But interesting fact with this kind of architecture is NaI0 means doping concentration of high VT transistor, IO transistor, is smaller as compared to the nominal transistor, right? And it is well known fact that and which is already I have verified in 180, 90, and 65 UMC technology. It is true that NaI0 is smaller than the Na core transistor or nominal transistor or nominal VT transistor, so that it is satisfying our requirement. Means I wanted to design a CTAT voltage, process independent CTAT voltage, so that I have taken two transistors. Delta VGS is positive and d delta VGS by dt is negative, so that we are ready to generate a CTAT voltage. And this is the circuit which we have designed. Startup circuit already we have studied how we can design. Here I have designed CTAT current generator. Here I have designed PTAT current generator, and here in middle part I have done some scaling. And I claim that this is a process VDD and temperature independent. We have fabricated this, and these are the measured results. Reference voltage is having some variation, that is plus minus 2.2 millivolt over the temperature range of 100 degree. And this is some AC response, right? This I have tested over across different dies, and this is line regulation. And summary of this is VDD is 1 volt, 180 nanometer, IDD is 15 micro, and surprisingly you can see that delta V reference is very small, that is approximately 4 millivolt over the temperature range of 180 degrees Celsius, 100 degrees Celsius. I think that's all here. I think we can see this tomorrow. And at the end conclusion, voltage reference is an integral part of any IC design. Therefore, understanding it is an essential part of a design. So that I think that's all. Thank you. And hopefully I have covered all the required thing or base for tomorrow. Tomorrow we can see some other extra interesting facts for voltage reference.
Thank you very much, Dr. Vinayak. Yeah.
Okay.
Any questions from the participant?
Any questions, please?
Hello, sir.
Yeah, please go ahead.
Sir, in 130 nanometer, for example, if we are using 130 nanometer technology, then what should be the minimum length? Means what can be the minimum length of MOSFET we can keep? Can we keep it as 130 nanometer, or we should keep it more?
Okay. Generally, it depends on the application. For in respect to voltage reference, which I am talking today, generally it is advisable to have a larger transistors or larger length transistors, right? Because it will avoid the problem related to mismatch and for the some extent process as well. So that it's better to have a higher channel length while designing a low frequency circuits.
Okay, and for amplifier op-amp?
Amplifier op-amp, if you're not very much concerned about the UGB, then as it is true for voltage reference, then you can have again similar larger length transistors as compared to a lower length transistor. But again, depends on the application. If your application demands like in a frequency, a PSNA particularly, you should have a very high PSNA at a very high frequency, then definitely you have to choose the op-amp of a or design op-amp which is having the channel length smaller, right? So that you can have a larger PSNA response at very high frequency as well.
Okay. So based on frequency, we have to select. So if it is high frequency, then we have to select small length.
Yeah, right.
Okay.
Smaller length, that means
Okay.
it will quickly pass its charges, right? So that smaller length means
Okay.
high frequency.
Okay. Thank you, sir.
Yeah, hello, sir.
Yes, Mr. Bose, thank you.
Yeah, I just would like to know, I mean, it is my personal query, just to ask you, is there any direct relation between the channel length of a MOSFET and threshold voltage adjustment? I mean, is this any direct relation? I mean, by reducing the channel length, it is somehow related how to reduce the threshold voltage of the device subsequently, or there is no such relation exist?
Actually, it is a quite interesting fact. I'll show quickly one slide so that I can, as I'm having time of 5 minutes.
Sure, please.
Yeah, I'll skip those slides with you. Fine. Here, you are saying something like, yeah, this slide will answer you more. This is valid in 180, 90, and 65, which I have already designed. Here, the interesting fact is that the moment you are reducing the channel length, your threshold voltage increases. And it is quite interesting fact, and in fact, surprising fact to me as well. And if you dig up a little, you will find that yes, why it is happening? Because it is happening of you are having some pocket implant and VT adjust implant, so that it is not always true that if you start reducing the channel length, your threshold voltage will reduce. It will increase in fact further as the channel length reduces because of the pocket implant. right? It is called as a reverse short channel effect. In fact, you might have studied, and you can observe it at a lower technology node as well.
So it is true for most of the cases, right?
I don't know all the cases, but whatever I have worked on, I know UMC 180, 90, and 65. I know it is sure.
Okay. Thank.
And in fact, 180 we have fabricated those things, those concepts, so that it's proven that it is working.
I think it is only true when all other relevant parameters of the MOSFET transistor is constant, like Na, dopant concentration, and oxide capacitance. When all other things are remain constant, then only I think this relation might be valid.
Yeah, right. If everything is constant, then if you reduce the channel length, your VTH will fall.
VTH will increase. Yeah.
Yeah.
Thank you. Yeah.
Thank you. Yes. Any other questions? Anyway, we are meeting tomorrow as well. You can skip the question and you can keep the question for tomorrow as well. It's not an issue. I think we are on time.
Yeah, just about time.
Okay, thank you.
Okay. Thank you very much, Dr. Vinayak. So we will stop this session here. We'll take a break. We will meet again at 2 o'clock. The next session will be on sample and hold circuits, which I will be taking.
Okay.
Yeah. Thank you very much, Dr. Vinayak, for the wonderful
you,
session on
Dr.
references.
Thank you, sir. Thank you, sir.
Thank you. Thanks a lot.
Okay,
Thank you.
thank you. We'll meet at 2 o'clock.
Okay. Yeah, bye-bye.